Hello my dear students, I hope you are doing great. So now this problem is really a tough one, tough in the sense that multiple concepts are involved here. So now let's see this problem and we will really tackle this problem, analyze this problem step by step. Okay, so what does this problem say? Let's see. A loop is formed by two parallel conductors connected by a solenoid with inductance L and a conducting rod of mass small m which can freely slide over conductors without friction here. Okay, this is the conductor, this is also a conductor, and these are connected with the solenoid, and inductance of the solenoid is capital L, and a rod is sliding over, this is the conducting rod, is sliding over these conductors, and mass of the rod is small m and length of the rod is small l. Okay, and magnetic field is given to be vertically into the plane. Okay, so into the plane is the magnetic field, and okay, at t is equal to 0 the rod is imparted an initial velocity v0. Okay, this rod is imparted initial velocity v0 here. So basically in this diagram I have shown here, initially the rod was here at x is equal to 0, and now the rod was imparted initial velocity v0 directed to the right. So towards right this rod is imparted, and what we need to find the law of its motion x as a function of time if the electric resistance of the loop is negligible. So no resistance is there in the entire circuit, then we need to find x as a function of time. Okay, so I have drawn the diagram over here, and we will be seeing how to solve this problem step by step. Initially the rod was imparted initial velocity of v0, so of course it will have some velocity v0, some velocity. Let's say the velocity of this rod is v towards right, some velocity is v here, this is the velocity of the rod. So if this conducting rod is placed in a uniform magnetic field, we know there will be a motional EMF. This is the first concept here. So the motional EMF we know is v cross b dot L is the motional EMF, and so it becomes v cross b dot L as vvl. And what is the polarity of the induced EMF? Of course the direction of v cross b is towards the y-axis, right, in this direction. So of course the polarity will be like this. Okay, this will be the positive polarity of the induced EMF, and this is the negative one. So the induced EMF is equal to vb small l. Okay, so if there is a induced EMF, then of course there is going to be some induced current here. Let's say current I is induced in this circuit, then what will happen? This current will flow through this inductor, then there will be induced EMF across this solenoid, and the induced EMF we know is minus L di by dt. So we can write Kirchhoff's voltage law, KVL, as this KVL as EMF E minus L di by dt is equal to 0. So EMF, induced EMF is V B L minus L di by dt, L di over dt is equal to 0. And from here we have this equation. So VBL is equal to L di over dt, and what we can do from this equation, see, what is our objective? Our objective is to find x as a function of time, and in order to find x as a function of time we need to know the acceleration, in fact. So the acceleration can be found using the force, right? And what is the force acting on this? So we'll be seeing all these things. So first of all, let's simplify this equation. V is basically rate of change of this position of this rod, dx over dt. So it becomes dx over dt into BL is equal to L di over dt, and we can see that we get rid of dt here from this equation. Then our equation becomes V L dx is equal to L di. So now we can write I as a function of x. So if we integrate it here, dx, integral dx is equal to L di integral d. So at x is equal to 0, when the rod initially was there, then current will also be 0. Why current will be 0? Because initially there is no flux linked with this solenoid, and we know flux does not change suddenly. If the velocity v0 is imparted to the rod, then flux will also be 0 instantaneously. just after imparting velocity v naught. So flux 0 means here current is also 0. So from 0, okay, initial current is 0 to some current value I, let's say, so 0 to x. So now we get current as a function of x. So I is equal to B L over capital L times x. So basically this is what we are trying to establish, because we want to find out magnetic force on this rod. And what is the magnetic force? We already know this concept. IL cross B is the magnetic force, and the direction of IL cross B magnetic force is equal to, what is the direction? IL cross B. See, I is in upward direction, right? So I is here, L cross B, and magnetic field is into the plane. So using right hand thumb rule, the direction of this magnetic force will be towards left, right? Magnetic force is equal to ILB. And we know this I, so I times BL, I times BL, okay? And if we plug the value of I here, we'll be getting B square L square over capital L times x is the magnetic force on this rod towards left. Okay, cool. We got this value of magnetic force. Now we can find acceleration of this rod using Newton's second law. So acceleration will be magnetic force over its mass, and magnetic force is this one over the mass, so it becomes B square L square over ML. M is the mass of this rod times the displacement x. Okay, this is the acceleration of the rod, and direction of acceleration of the rod will be towards left. We can easily see that it will be towards left. So this is the acceleration of the rod, and acceleration is basically opposite to the displacement of the rod from this position, initial position. And now we can observe this equation to be the equation of simple harmonic motion, because acceleration is directly proportional to displacement of this rod from this main position. Okay, because how we can say that this initial position is the main position? Because no current is flowing here, so ILB will be 0, right? So no magnetic force will be 0, and hence that position will be the mean position. And we can also observe that the direction of acceleration is opposite to the direction of displacement of this rod. Well, so we have this acceleration as a function of x, which is nothing but SHM's equation. And we already know that this is omega square, right? Omega square is this one. Omega is angular frequency of simple harmonic motion. So basically what will a rod do? This rod will oscillate back and forth about this main position. So initially it will have velocity v naught towards left, okay, maximum velocity at the main position, and then rod will come to rest momentarily, then it will go backward, and then again to the left, and then again it will oscillate back and forth like this. Okay, so this will be your omega square, so that we have this omega as BL over square root of ML. Okay, so rod is at mean position initially, so we know x is equal to a sine omega t when the rod is initially at the mean position, where capital A is the amplitude of this rod, which we don't know right now. We will be finding it out. So it is a sine of omega t. And how we can find this capital A, which is the amplitude? See, using this relation, we know that velocity in SHM can be written as omega square root of a square minus x square. Okay, so initially we know the velocity of the rod as v naught. So here if we plug it, it becomes v naught, and we know the value of omega, which we already calculated here. Omega as b l over square root of ml times x is 0, because at x is equal to 0 only velocity is v naught, and square root of a square becomes a. Then we can write amplitude a is equal to v naught square root of ml over bl. Okay, we got the amplitude, this thing. And if we plug the value of amplitude here in this equation, we will get our final answer. So this is basically the final answer, where amplitude is given by this one and omega is given by bl over square root of ml. So finally our equation becomes, x as a function of time becomes v naught square root of ml over bl a sine of omega t, and omega is given by this one, omega t. So this is the final answer. Okay, x as a function of time. So many concepts are involved in this problem, you can easily see. So let me recap what are those concepts involved. So first concept was this one, V cross B dot L. So this is the motional EMF, and then we have EMF as VBL. We simplified this one, and then we applied KVL, Kirchhoff's voltage law, in this circuit. Then it becomes VBL minus LdI by dt is equal to 0. Then we went on simplifying it, we got rid of dt, then we expressed I as a function of x in order to find magnetic force as a function of x. So magnetic force is ILB, then we plug the value here, I, value of I, then we got this magnetic force, and then we applied Newton's second law, then we got acceleration as a function of x, then we observed that that is the equation of simple harmonic motion with angular frequency given by this one, and finally we could see that x as a function of time in SHM is given by this one, x is equal to a sine omega t, because at t is equal to 0 the rod is initially at the mean position here. So now we need to find capital A. How we can find this capital A amplitude? From this relation in SHM, velocity as a function of displacement, or displacement from the mean position. So here initially the velocity is V0 and x is equal to 0 initially. So now we got this capital A amplitude, and then we plugged this back into our equation. We got x as a function of time. So I hope you got it very well. If you have any kind of confusion, then do comment below. Let me know. I'm going to answer your query definitely. Thank you, students.